want to say is today your sign up is due. Okay, so I have 5 people here that haven't signed up for a group. That's due today. Okay, everyone else signed up, so you're good there. So please sign up. All right, chapter, so this example 8-14E, we have saturated steam is generated in a boiler by converting a saturated liquid to a saturated vapor at 200 psia. This is done by transferring heat from the combustion gases, which are at 700 degrees Fahrenheit, to the water in the boiler tubes. Calculate the wasted work potential associated with this heat transfer process. How does increasing the temperature of the combustion gases affect the work potential of the steam stream? And they give us the dead state temperature of 80 degrees Fahrenheit, the dead state pressure of 14.7 psia, and then they give us a schematic. All right, so we're given water. We have a quality of 0, so it's a sat liquid. And then state 2 is a quality of 1, so it's a sat vapor. Okay. The pressure, it says, is being converted to saturated liquid to a saturated vapor at 200 psi. Okay. So the pressure at 1 and 2 are 200 psi. Okay, and it's like a flow channel, so the pressures are the same there. The combustion temperature is 700 degrees Fahrenheit, which is 1160 Rankine. We have a dead state temperature of 80 degrees Fahrenheit, which is 540 Rankine. We have a dead state pressure, which is 14.7 psia. They want us to find the X destroyed, okay, which is the weight. I should also make this lowercase x destroyed. Because that's the wasted work potential. It's lowercase because it asks for work and not power or rate, right? So it's wasted work potential. Okay, I'm talking about X destroyed. And then how does T combustion, temperature of the combustion, affect the work potential of the steam stream? That's the work potential is the exergy of the steam stream, which is the flow, change in flow exergy. All right, our schematic. Basically showing kind of like one boiler tube. We have some heat transfer. Draw our boundary. From 1 to 2. Assumptions. All right. So first off, we're trying to solve for X destroyed. All right. So where can we start to solve this?
Conservation of mass.
Conservation of mass. Be there. Steady state. Right? So the mass stored at 1 is equal to 2. Okay. Where else do we go to, or where can we go next, or where do we start with getting this X destroyed?
Conservation of energy.
So conservation of energy. What are we getting out of the conservation energy for this?
The H, right?
Huh?
H.
H?
Yeah, H at 1 and 2. Entropy.
Okay.
It will give us the heat, right? Heat transfer.
Yes. All right, so COE open system, right? All right, we said steady state. What other simplifications?
We can assume mass flow rate's the same, so velocity is the same, and there's no change in height, so kinetic and potential.
Yeah, so neglect kinetic and potential. Is there work on our system crossing our boundary?
No work.
Yeah, there's no work. All right. All right, so we have all right, so we have a relationship for the rate of heat transfer. What do you guys want me to do with this?
We can find the H values because we know it's saturated liquid, saturated vapor at the 200 pressure.
All right, so we can do our states. We have fixed states. So state 1, pressure 1's 200 psi. We have a quality 0. State 2, same pressure, but the quality is 1. So we can get H1 and H2. Okay. All right, so we have our enthalpies. What about the mass flow rate? So unsure. All right. So I have through the group chat, someone said open system exergy balance. That's a method to get, there's also two other methods to get to the X destroyed. Okay. So what you'll see is there's three different paths there. So if we look at the general layout, X destroyed, what's that equal to? Does anyone remember from the lecture notes?
T naught S gen.
Yeah, T naught S gen, which is also equal to work reversible out minus work useful, or work useful in minus work reversible in. This is work producing. This is work consuming. Which one do we have? That's a tough one, right? So if we look at our diagram, there's no work, right? So it's not work producing or work consuming, but we could just look at it and just say, oh, it's a work producing device, but work useful is 0. So then our X destroyed would just be work reversible out. Okay, so the three methods. We have X destroyed, which was mentioned, which is what we're being asked for, but I can't draw a bracket. All right, so that's from, mention the Exergy balance. Okay, we have T naught S gen. How would we go about that one?
You would have to calculate S gen using entropy balance.
Yeah, so this one's the entropy balance. And then this one is the Exergy balance for work reversible. Which has X destroyed equal to 0 when you solve for work reversible. Okay. So that means we have 1, 2, 3 methods of actually solving for X destroyed in this problem. Okay. I'm only going to do 2. I'll save the third one for a different problem. All right. So I had the Exergy balance one, and we'll do that one. I'm going to save that one for the next, but we'll do the first off, the one that everyone's a little bit more comfortable with, the entropy balance. So we got entropy balance, open system. Oop, and I'm just crossing it right out. Making it impossible to read. Good enough. All right. So we already said steady state. We have heat transfer, right? What's the temperature of that heat transfer? So we go back to our schematic, and that's the temperature right here, right? The temperature at which we're crossing the boundary. and that's going to be T combustion, okay? Because they're asking for the wasted work potential associated with this heat transfer process. So they want you to include the heat and the temperature with that heat, okay? So that's not the dead state because it's in a boiler, right? So that boiler is creating that heat at that temperature. Okay, other devices, if you make the boundary bigger, it could be the surrounding air then, but this is inside a boiler, this tube where the water's going. So inside the boiler, there's combustion that's heating up that tube. All right, so we have then we have this, and then if we apply our conservation of mass, you have this. All right, so what's the next step?
We can get the entropy values from the tables.
Entropy. So we still need, let's go through. Yeah, we can get S1 and S2, right? So we go back up, state's fixed. So we can go get those, okay? All right, so now we have S1 and S2. We have T combustion. We need this. Those three are unknown. What are we looking for? X destroyed, right? Is it the rate of Exergy destruction, or is it just X destroyed? Yes, so it's the rate, or it's not the rate, right? So we're just looking for lowercase x destroyed, which is T naught lowercase s gen. Doesn't have a dot on that s gen, right? So what can we do to this equation to get to this version of s gen?
You could divide out mass, the mass rate.
Yeah, so divide out mass flow rate on across everything. Okay, so that would get us little q, T combustion, S1 minus S2, and then that gets us lowercase s gen, okay? Now I have S1, S2, we have T naught, so we need S gen, right? To solve in this, we have T combustion, so we need our heat transfer per unit mass. So we already started on that path earlier, right here. Okay. Can we get our lowercase q?
Yeah, again, divide out by mass.
Yeah, divide our mass flow rate again, okay? Okay, and we get 843.3 BTUs per pound mass. Okay, so now we have Q, lowercase q. So the only unknown in this equation is S gen, so we can solve for entropy generated. 0.2752 BTUs per pound mass R. And then we can utilize T, multiply T by T naught and get the actual wasted work. So we get 149 BTUs per pound mass. So if we multiplied that times mass flow rate, so scaling the system, small versus large, small system, small mass flow rate, large, we would get the BTUs per second, right? The power that's lost. All right, so that's what we were asked for. So that was entropy balance. Okay, so let's do the Exergy balance method. Open system. I'll do the general one first. Okay, we have what's crossing our boundary, what's going on inside our boundary, and then the destroyed, right? Mass flow rate carrying in, Exergy, mass flow rate carrying out. We have our X destroyed. All that's equal to the change in Exergy with respect to time. Okay, so we got our new equation. What can I cancel for our problem? Steady state. Okay, so this goes to 0 on the right. Anything else? Volume. So it's not growing. Our control volume is not growing or shrinking. Okay, so that goes away.
There's also no work.
Yeah, there's no work on our actual device. Right. All right, I think that's where we're left. All right, so we have a heat transfer. Mass flow rate at 1 is carrying in Exergy, 2 is carrying out Exergy. We have our X destroyed. Put our mass flow rate together. Now what?
Again, divide out by mass rate.
Yeah, divide out by mass flow rate. All right. So we have our dead state temperature, temperature combustion. We already went down the path of finding our conservation energy, but if we started here, we would know, okay, go to conservation energy, get our lowercase q. We're, oh, why did I make that? It should be lowercase x. Okay. That's what we're ultimately trying to solve for with this method. So then we need our flow exergy change. Okay. Okay, so we have this. There's also a change in kinetic energy plus change in potential energy, which we're canceling, right? All right, so with this, we've already figured out enthalpy values and entropy values, and we have T net. Is there a question, comment? Okay. Plug those in, we get negative 302.1 BTUs per pound mass. Okay, so that means we then have this term, this change in flow exergy. So then the only unknown is our X destroyed, and we'll get the same thing, 149 BTUs per pound mass. Okay. So we did this method too, the first method. Third one, we would just go down the exergy balance and solve for reversible work. So we would start here, but this all in the work brackets would be reversible work, but the X destroyed term would go to 0. Okay, so in this case, we're just swapping the two. And when we got down to here, you would see X, that work reversible is going to be equal to this heat transfer part and the flow exergy part, instead of it being equal to the X destroyed. Okay, so that would be the 3 methods of getting this. Okay.
I'm a little confused for the third, I guess, way you would solve it.
The third method, you don't kind of mix them two together, because the third method, it's the exergy balance, and I'll do it on the next problem, but the exergy balance, but we're solving for work reversible now, and X destroyed is equal to 0. So when you start with the exergy balance, the heat term will be there, but the work term will be there, but it'll be called work reversible. Okay, we canceled that out on the actual one because the actual one didn't have any work. But on this reversible one, now you have work there, and then you have flow exergy entering and leaving, but there's no X destroyed because it's now reversible, so it's 0. Okay, so you would just solve, and you would end up seeing that work reversible will end up being equal to this. If you go down that, which we'll go through the steps for doing the work reversible on the next one. But if you go through the exergy balance and do that, you'll get this.
Okay.
Okay.
I have a
The other,
quick
oh,
question.
go ahead.
So the temperature combustion, how
Yeah.
did you know that it was like on the outside, like the immediate outside of the
Well, it's a boiler, so you're in a boiler, you just got tubes of a fluid, like water flowing through it, and then you're adding just it's basically combustion fluid there. So it's just, if you're using natural gas, it's the natural gas exhaust that's right there on the tubes. Okay, so this is done. So when they're saying this is done by transferring heat from the combustion gases, which are at 700 degrees Fahrenheit, to the water in the tubes. And then they want basically to calculate the wasted work potential associated with this heat transfer process. So the combustion gases are on the outside of the tubes, and they want us to include that because they want the information about that heat transfer process too, and not just the flow exergy part.
So could you say that the water is at 700 degrees Fahrenheit as well?
No. So the water will be at the saturation temperature of 200 psi. The water's linked to that pressure.
Oh, okay, I see. Yeah.
Yeah, think like when you got water on the stove, right? The element that you're heating with is way hotter than the water, right? The water is still, when you get to boiling, it's still boiling temperature, even if the heating element's way above it, right?
Yeah.
Okay. Other questions? The other thing to think about is if we were doing the second law efficiency, we can think about what's exergy expended, what's exergy recovered, what's exergy destroyed. This is expended because that's in, because that ends up being positive. We're putting heat in, putting work potential into the system. We're expending exergy. We're recovering exergy in the flow exergy because that was negative, right? You saw negative 302.1, so that's our recovered exergy. And then this is the destroyed. And we could set up our second law efficiency of this system just from that. Okay, that's why I say the exergy balance, setting it up, you can figure out any of the second law efficiencies just by doing that. All right, the last part of this problem, kind of, not a huge fan of this question, but it says, how does increasing the temperature of the combustion gases affect the work potential of the steam stream? And it goes kind of with what one of the questions that just happened. How does this affect this, right? And if we go down, when we look at the flow exergy, that temperature of the combustion is not there at all. So it doesn't affect it at all because you have state 1 and state 2 that are, that's all that tells us about the linking of combustion temperature. The combustion temperature is in the flow, is in the heat transfer exergy. That's the only place where that combustion temperature is in. So that affects the exergy from heat transfer, but not what the flow exergy is, okay? So it'll affect the X destroyed, but not the flow exergy. All right, let's do, unless there's another question, let's do 8-39. A 0.8 meter cubed insulated rigid tank contains 1.54 kilograms of carbon dioxide at 100 kPa. Now paddle wheel work is done on the system until the pressure in the tank rises to 135 kPa. Determine A, the actual paddle wheel work done during this process. B, the minimum paddle wheel work with which this process between the same end states could be accomplished. Take the dead state temperature to be 298 Kelvin, and then they have the schematic. All right, so we have CO2, it's an insulated, rigid tank. We've got a volume, 0.8 meters cubed. We got initial pressure of 100 kPa. We got a second pressure of 135 kPa. We got the dead state temperature of 298 Kelvin. They want us to find the paddle wheel work, the actual paddle wheel work. And then part B is the minimum paddle wheel work with which this process between the same end states could be accomplished. What are they asking for with that?
Reversible work?
Yeah, so they're asking basically for the reversible work. Okay, because this is a work-consuming device, so they're working for that minimum work. All right, so let's do our schematic. We got my beautiful rigid tank. Paddle wheel work, and then it's insulated. Okay, we have CO2 inside here. Assumptions. All right, so for solving for the paddle wheel work, where would you like to start? It's an ideal gas, yeah. So we can assume, since we're looking at the substance is CO2, right? So it's at atmospheric conditions. CO2 we can assume ideal gas, okay? We're neglecting potential energy, okay? And kinetic. Okay. All right, so what equation do we apply to get paddle wheel work? Just a chapter 4 problem, for at least for part A.
Conservation of energy.
Yeah, so our COE closed system neglected kinetic potential. What about heat transfer?
Well, it's isolated or insulated, so
Yeah, so
I don't.
Yep. So we can assume adiabatic. That's well insulated, okay? So that gets rid of Q. All right, so then we're left with the only work term we have is paddle wheel work. There's no boundary work, right? It's a rigid tank. So we have mass times delta U, okay? And we can move this around, get rid of that negative sign. Flipping U1 minus U2, okay. So they gave us, oh, and I forgot to write it down. Oops, in the givens, they gave us the mass, okay? So we also have in our givens, mass is 1.54 kilograms. I don't think I missed anything else, no. All right, so they give us the mass. All right, how do we get the change in internal energy?
We can use the ideal gas law.
The ideal gas law,
well, not the law, but the
Relate?
relationship, because it's a constant volume.
Yeah, so we can use, since we know it's an ideal gas, delta U is equal to CV delta T, and delta H is equal to CP delta T. Okay. All right, so that means we have CV T1 minus T2. Okay. Again, we have the mass. We need to get CV. We don't have T1 or T2. So how do we get those? Oh, from the ideal gas equation. Okay. So let's see the ideal gas. PV equals mRT. And if we do this for state 1, we have pressure 1, the volume's the tank, so it's just volume. T1, we have volume, we have pressure 1, we have mass. We just need to get R for CO2. 0.1889 kilojoules per kilogram K. So that's table A-1. Okay, so then that means we have R, so the only unknown is T1. So we get 275 Kelvin. How do we get T2?
Same equation.
Yeah, same. So the same thing. And our only unknown is T2. You could also, from that same equation, set what stays constant. So if you rearrange the ideal gas law, T over P is equal to volume divided by mass times the gas constant. Well, in this process, since it's a rigid tank, everything is constant. So that means on the right, so that means T1 over P1 is equal to T2 over P2. So you could also get it that way. It still is the ideal gas law. Okay. And solve for T2. All right, so now we have T1, T2. We just need CV. CV is at the T average. T1 plus T2 divided by 2. 323.1. So we get 0.68. So A to B. All right. So now we can solve. Right? So we get negative 100.8 kilojoules, which is working for the paddle wheel work. Okay. Questions? Okay, so we have the paddle wheel work. Okay, so now we need reversible work. Okay. So what do we do to get that? Exergy balance, closest Yeah, so let's do the Exergy balance. Closed system for work reversible, right? Cancellation. What are we canceling?
Volume or
Yep.
change in volume.
Yep. The rigid tank, so the volume's the same. Anything else?
Heat transfer.
Yeah, there's no heat transfer, right? So this whole term goes out. Now let's write it. So it's just the change in Exergy inside the system. Oh, no, we're doing work reversible. Sorry, I started going the other way. All right, so this is where the simplification. So
we're doing. My bad. You go ahead.
yeah, so it's for work reversible, right? So that's the case where this is canceled also, okay? So there's no extra and then this all right here just becomes work reversible, okay? Doesn't matter whether the volume's the same or not. It's just work reversible. If we were doing this process reversibly, okay? All right, so then we have work reversible is the change in Exergy, okay, of our system. Get rid of that negative sign. The per unit mass of the non-flow Exergy. So the question, yeah, if we were doing the Exergy balance and we left in X destroyed, yeah, now that work is the actual work because there's being work that's destroyed. So we would be, you know, you could ultimately, if you really wanted to, if you had everything else, you could solve for the work from the Exergy destroyed balance if you knew everything else, right? All right, so we're looking for work reversible. We have the mass. We just need to get our non-flow Exergy. Okay. We have no volume change again. We already used delta U, all right? That's CV T1 minus T2. Now we got to figure out delta S, right? And it's just another property change, right? So we have an ideal gas, just like we went and got for delta U, we got the relationship for the ideal gas of how to get those properties. Again, we have an ideal gas for delta S, we go, right? And we've did CV delta T, so we assumed, I forgot to write that down, but we were assuming constant specific heats, right? All right, so that means we go to delta S for an ideal gas with constant specific heats, and we have two versions of the equations to use. I'm going to use the CV version. That looks like that, okay? Because that allows me to get rid of this term, the natural log of 1, because the volume's the same, is equal to 0. Okay. All right, so we have then this left. So mass we have CV, T1, T2, we have the dead state temperature, we have CV, we have T1, we have T2. So we have everything there to solve. So our work reversible is then negative 7.18 kilojoules work in, right? So we, in the actual case, it was 100.8. In the reversible, it'd be negative 7.18. So the work was negative 108, 108.8, 100.8. And now we have 7.18. All right. Any questions on that? So the last thing is that I wanted to mention is you could also solve this problem 3 different ways, right? If we set up that same setup of X destroyed is T naught S gen, which is work reversible out minus work useful out, or work useful in minus work reversible in, right? We are solving for work reversible in, right? So we did this one. It's a work consuming device, so we would use this version if we're using it, right? Well, we solve directly with the Exergy balance for work reversible with X destroyed equal to 0, right? Well, we could easily have, because we have the work of the paddle wheel, right? We could have easily solved for T naught S gen and then just moved the paddle wheel work over and used that to solve for work reversible in. It's just algebra, not energy. So this is entropy balance. So we could have used that and then just with the paddle wheel work in this term, use that to solve for work reversible in. Or we could have solved for X destroyed. And that's the Exergy balance. And subtracted the X destroyed from the work useful, which is the paddle wheel work, and we would have got the reversible work in, right? So it's got 3 ways to solve it too, right? We already have enough to even solve for, if we needed to solve for X destroyed now, you know, 100.8 minus 7.18 would get us the X destroyed, the amount of wasted work potential during doing this process. Okay. All right, so I think I went just a minute over, but if you have any questions, let me know. And that's it. We'll do more examples next class. Okay. All right, I'll see you on Wednesday then. Or Monday, sorry.